So good morning, everyone. Welcome back to Math 115. So today we are going to talk over some more of section 5.5, and maybe we'll do a little bit of 6.1. So what I decided yesterday, actually what I looked up yesterday, was the rules regarding quizzes. So even though it was going to be a group quiz, I decided to not have the quiz today because for our class, which meets 4 days a week, apparently we're not supposed to have any kind of assessments in the last 3 days of class. So today is the third to last day of class, so no quiz. What that means for your quiz grade is that it will be just best 4 out of 6, basically. So I'll still drop 2. So whatever your quiz average is in Blackboard right now is your final quiz grade, unless you do the extra credit between now and the end of the semester, in which case it'll go up by 2 points. So 2-point increase on a 40-point grade is pretty significant. So, to the tune of like 5%, 4 or 5%, right? So I recommend that you do the extra credit if you want to raise your quiz grade a little bit more. Regarding the homework, you have 3 homework assignments due today, but 5.3 is really short. It's like 3 questions long. So those homework assignments are due today, and if you need an extension, just email me. I'm flexible on that, but I'm hoping that you can have those done so that you can sort of focus more on 5.5 and 5.6, which, by the way, I decided to not have a 5.6 homework. It's just too much stuff for 1 week. So we're going to have the 5.5 homework will be the last homework. So no quiz today, no 5.6 homework. Let's see. Regarding the final exam, first of all, I'm not going to put Chapter A on the final exam. It's going to be Chapters 1 through 5 and then 6.1. And my office hours are going to be this week in LeConte 109. That's what I'm hoping to do. There's some issues with the room where they haven't gotten my reservation right, so it's kind of annoying. But I'm hoping that that's going to be where we have our office hours. So we're going to start reviewing for the final exam today in office hours. And I'll try to record those sessions so that even students who can't make it to office hours can benefit from that. And I'll post them to my YouTube channel. If you can't, or if you want additional help, go to the tutoring center. I expect there will be lots of people there this week studying. You can find other people in Math 115, or you can find an instructor like myself or someone else who can help you in the tutoring center. So that final exam is going to be December 6th, which is a week from today at 9 a.m. in this room, close-up 201. And you can have a 1-page formula sheet, 8x11 letter paper. So tomorrow maybe I'll talk about what I would recommend you to put on your formula sheet. But it's things like, the order in which transformations should be applied. Things like sum and difference formulas, half-angle formulas. I don't know. Why don't you all tell me what else should go on the formula sheet? Sure, put the unit circle on your formula sheet. Or you can, put on like the formulas for interest, compound interest, right? You can put those on there, or how to get half-life and doubling time and all sorts of stuff like that. Yeah.
Can we also put examples?
Yeah, you can write whatever you want on your formula sheet. Log rules, that's another one I would put on there, is log rules. So stuff like that, but we'll talk more about that tomorrow. I'll give you a more complete list. Also, please complete the course/instructor evaluation. That really helps me out to improve my teaching. Okay, any administrative questions before we start in on content for today? Did you bring some for me? I'm not trying to shame you. You can eat in this class. I don't care. Okay. Doesn't seem like there are any questions, so let's move on to content for today. So what we're going to talk about today, I basically am just at a point where I feel like I taught you everything that I want to teach you, for the most part, which is why I pretty much am going to stop. What we're going to do today is really nothing new. Okay, a couple things that are new. We'll do a little bit of right triangle trigonometry, but yeah, we'll get to the mountain. Yeah, I wanted to have a real life application for you, so we're gonna do something with that mountain later. But let's start by reviewing what we were talking about last time, which is trigonometric equations. Now, this is something that I do think is important for you to know if you're going to go on and take a calculus course, or if you're going to go on and take differential equations or something like that. You should know how to solve trigonometric equations. So what are they? They're different than an identity in the sense that they're not always true. So solving an equation means to find out when it is true. And that means to find the inputs which will cause the equation to be true or not true. So for trigonometric equations, typically we have a list of infinitely many solutions, right? And because these functions are periodic, so we expect whatever solutions exist in 0 to 2 pi are going to exist in 0 to 2 pi plus 2 pi n, right? So add any multiple of 2 pi, you're going to get the same angle. And so these solutions are going to repeat over and over and over again because these functions are periodic. So last time we saw this mega example of this problem, which is about as hard as these problems can get, I think. So this is a problem that incorporated many different ideas. First of all, we had a trigonometric identity to get everything in terms of cosine. And then we noticed that this equation with cosine was quadratic in form. Okay, so the thing about quadratic in form is you can solve the corresponding quadratic equation. And then if, whatever your translation is, okay, in this case it was x equals cosine theta, then you can solve for x and then just set cosine theta equal to whatever is the solution to this quadratic equation. So we did that, and we got two equations. The first was cosine theta equals the square root of 3. We determined that this is not a valid equation, or rather it will never be true for any value of theta, because cosine always gives outputs which are between -1 and 1. Square root of 3 is larger than 1. It's something like 1 point... I don't know what it is. It's something like 1.6 or something like that. I don't know. Anyways, it's bigger than 1. You can tell that it's bigger than 1 because the square root of 1, it would be 1. Anything bigger than that is going to have a larger square root. Okay, so this one we got rid of because that's not possible. The other one, on the other hand, we said, well, I just need to find an angle theta which gives us negative square root of 3 over 2 as an output for the cosine function. Now the output for the cosine function is of course the x value. So I'm looking for the intersection of the unit circle with the line x equals negative square root 3 over 2. And there are 2 points on the circle which intersect this line. And we describe the angles which point at those points, namely 5 pi over 6 and 7 pi over 6. And so we ended up with something like this, right? Except this wasn't the full story. Why was this not the full story yet? We found the angles which caused this equation to be true, didn't we? Why am I not done at this point?
Because there are also coterminal angles.
Exactly, because these are 2 angles such that if you plug them in here, you get this answer, right? But also any coterminal angle, namely any angle like this angle plus 2 pi, or this angle plus 4 pi, or minus 2 pi, or minus 4 pi, or minus however many even multiples of pi, right? So we can have many, many coterminal angles which will give us the same result for the cosine function. So I need to list them all. The way I list them all is by using set builder notation. So that looks like the following. Okay, we say, look, theta is an angle such that theta is 5 pi over 6 plus a multiple of 2 pi, okay? Plus a multiple of 2 pi. So this is like a bucket, and we put into our bucket angles like 5 pi over 6, or, what do we add, 12 to it? 17 pi over 6, right? Or 29 pi over 6. We throw all of those into the bucket, right? And then also we're going to union, meaning we're going to combine the members of this set with the members of this set to make a larger set, which contains all of the angles which are of this form or of this form, right? Okay, or of this form. Remember, union, loosely speaking, can be thought of as an or, okay? So theta should be a member of one of these two sets or both. Okay, so that was the giga problem. Any questions on the long trig problem? Okay, I thought I'd show you one more, which I think might be on your homework. So hopefully this helps you with that. Actually, we're not doing partner practice today. I'm going to solve this for you. Even though I don't think that's as productive, we're not doing partner practice today. Okay. I'm going to switch to blue. I like blue better. Okay, so this one looks kind of crazy, right, when you first look at it. But let's break it down into what this really is. We have one thing being multiplied with another thing. And that's equal to 0. So we had something called the zero product property. You remember what the zero product property said when we were multiplying two things together and we get 0? What was the zero product property about? Yeah, it says, look, if I take two numbers and I multiply them together and I get 0, then at least one of those numbers has to be 0, right? So this is like a factored quadratic kind of a thing, right? We have two binomials being multiplied together. We can just take each of these equations and set it equal to 0, or each of these expressions. So 2 sine x minus 1 equals 0, and, or square root 3 tan x minus 1 is equal to 0. Because we take two numbers and multiply together and get 0. If they're not both 0, then we're not going to get 0 as the output of their multiplication. Or if both of them are not 0, excuse me. So we need to set each of these equations equal to 0 in order to solve this one. So how am I going to handle something like 2 sine of x minus 1 is equal to 0? That feels kind of intractable in the current form. How can I make it look better? Yeah, add 1, divide by 2. Okay? The reason this feels bad is because you're like, well, you're trying to think of like, oh, well, like what does sine need to be in order to get multiplied by 2 and then subtract 1 and get 0? No. Just move that stuff over so that we have sine of x is equal to, if I add 1 and then I get 1 and I divide it both sides by 2, I get 1/2. Now this is more friendly, right? I just need to know when is sine of x equal to 1/2. And we can solve that fairly easily by looking at the unit circle. Okay, remember sine gives us the height of a point on the unit circle. So I want to find points whose height is 1/2, okay? That's what I want to do. So let's do that. Do one of these. So what are the 2 points which I'm looking for? They are in the first and second quadrant, namely this one and this one. Okay, and what do I know about those points? I know that the y-coordinate is 1/2. So I'm going to draw some triangles in here in order to figure out what the x-coordinate of those points are. And really, in order to find out what are these interior angles, like this one and then this one, that's what I want to know. So if this is 1/2 and this is 1, I can use the Pythagorean theorem to find out that this length should be the square root of 3/2. So this is going to be the square root of 3/2. And this triangle looks exactly the same, except the x-coordinate will be flipped. So these are the 2 points, okay? And I know that if I have a triangle whose side lengths are 1/2, square root of 3/2, and 1, what kind of triangle is this? It's one of the special ones. Yeah, this one's a 30, 60, 90 triangle, okay? So in this case, which angle between angle 1 and angle 2? Which one is going to be, or sorry, not angle 1 and 2. This one is angle 1, and this one is angle 2. Which one is going to be the 30-degree angle? Yeah, angle 1 is going to be the 30-degree angle. And I don't ever want anyone to rely on, like, what does the triangle look like, okay? Because you might draw it not so accurately, right? Is there a question? Question?
No.
We good? Okay.
Yeah, I'm good.
All right, so I don't want anyone to have to rely on just looking at the angle to visually identify that it's 30, 60, 90. I mean, I try to draw them as accurately as I can because I have the sort of the foresight of that, but your triangle might look kind of more like this, in which case you could get confused. So what I want you to rely on is what is the side length that is across from the angle, okay? That will tell you much better of like what that angle is than just looking at it, because you might not draw it very accurately, right? So in this case, 1/2 should always be across from the 30. 60 is across from the square root 3/2. Okay, and so what is the input that is going to create this is x equals to pi/6. Or x is equal to, what's this one going to be? This is going to be, okay, the way I think about this is pi takes us all the way to here. I need to go pi/6 less than that. So that's 5 pi/6. Okay, and then, of course, we're going to say plus 2 pi n plus 2 pi n. Right? So we could say, look, x, we're going to talk about the set x such that x is equal to pi/6 plus 2 pi n, and then comma n is in z. And we will union that with the set x such that x equals 5 pi/6 plus 2 pi n, n is in z. Okay, so this is how we could describe the set of x values, which will cause sine x to be 1/2, which will cause this factor of the equation to be 0, right? Because we would do 2 times 1/2 minus 1 is 0, okay? So these are the inputs, such that if you plug them into right here, you get 0 for this first factor and then something else for the other one. It doesn't matter what the other one is, because then the whole thing will be equal to 0. The equation will be satisfied, right? Are there any questions about how we did that one? I think we have actually done that example, just this part, of sine x equals 1/2. I think we did that last time, or maybe the time before it. I'm not sure. Are there any questions on that? Okay. It doesn't sound like there are, so let's handle the other piece, which looks a little harder. So I'm going to do the same process here and move everything over. Tan of x minus 1, or sorry, is equal to 1 over the square root of 3, right? So this is a little bit more difficult to identify what this number is, or what is the corresponding point on the unit circle. So let's see if we can figure it out. I'm going to draw a unit circle. So I know that the value of tangent is positive, so I know I'm going to talk about an angle which is either pointing into the first quadrant or pointing into the third quadrant, right? So the angle is going to be like one of these ones, okay? One of these ones. And we're supposed to find out what is this angle theta here, right? Or what is this angle alpha? Okay? We want to know what are those two angles, which produce a point on the unit circle. And what do we want? Tangent is going to be the ratio of y divided by x. So we do y divided by x, and we get 1 over the square root of 3, which means we could rewrite this equation as y times the square root of 3 is equal to x. Which means that what? That we're going to have like a 30, 60, 90 type of triangle where, let me go to a different color, where this length, x, okay, is going to be longer than the height, right? The x value is bigger than the y value. So in order for that to be true, this would need to be 1/2, this would need to be 1, and this would need to be the square root of 3 over 2. Whoa, that 3 got kind of wonky. The square root of 3 over 2. Does that make sense how we figured that out? Okay, it's to say that, okay, if you wanted to be even cleverer, you could say, I know that x and y satisfy the Pythagorean theorem. So I'm going to say, look, x squared plus, sorry, not x squared. I'm going to take y times the square root of 3, put it in for x. Okay, then I would get y times the square root of 3 squared, that's my x squared, plus y squared is equal to 1. And then you'd get 3y squared plus y squared equals 1, 4y squared equals 1. Therefore, y is equal to 1/2, or negative 1/2. Okay? So that's how you can figure out what the y value is if you don't have this sort of, without having to do this spatial reasoning. But okay, so what is the angle inside? This angle is, again, pi over 6, right? Because pi over 6 points at a height of 1/2. So I think we have theta equals pi over 6. And then, of course, tangent is going to take the same value down here, because the x and y will just be negatives of one another. The negatives will cancel when we divide them, and we're going to get the same exact thing. Another way of saying that is that tangent is pi periodic. It takes the same value after an additional pi radians. Okay, or theta equals, so if we add pi to pi over 6, I think I'm getting 7 pi over 6, right? And of course, plus 2 pi n, plus 2 pi n. Okay, so what do? We are going to take 4 sets. We take these sets here, which came from sine x equals 1/2. We're going to union them with 2 other sets, namely theta such that, oops, I switched for some reason to theta. Should be x. X such that x equals, and guess what? I'm not going to rewrite this thing, because those angles are already going to cause sine of x, 2 sine x minus 1 to be 0. So I don't need to rewrite this set because I've already included all of these angles. All that's left to do is to add the ones that are not present in the other set, which means I'm going to take 7 pi over 6 plus 2 pi n, n is in z. Okay? So we have to union together 3 different sets. What does it basically describe? This describes all of the angles, okay? All of the angles which point here, here, or here. Okay? This is kind of what this is describing, is all of the angles which point at one of these 3 points on the unit circle. Okay? It turns out if you point at this point, pi over 6, then the angle will cause this to be 0 and this to be 0, and then 0 times 0 is 0, right? If we're pointing at 5 pi over 6, or something coterminal to 5 pi over 6, then what? Then this one will be 0, and this one we don't know, but it won't be 0. If we are pointing instead at 7 pi over 6, then what's going to happen? This one will be 0, this one will be non-zero. Okay? So we found all of the x values which will cause one of these two things to be 0, or both of them to be 0. Okay, any questions on this example? Yeah.
Make sure I'm kind of tracking here. So could we have on the right side with the tangent example, could we have written that as pi over 6 plus pi n? Would that have covered?
Yes, yeah, absolutely. There's many different ways that you could adjust this. So you're exactly right. So what Ashley has pointed out to me is that, look, you already figured out that tangent takes the required value here, and you know that tangent is pi periodic. So you know if you just add pi, you're going to get a point with the ratio of the y to the x is going to be the same. And then also if you add pi again, you're going to go back, and then you're going to again get the same tangent value. So rather than write both of these two values and then add 2 pi n, since these two values are exactly pi apart, we could instead write x equals pi over 6 plus pi times n. Instead of 2 pi, we're writing plus n pi. So we add any multiple of pi, odd or even. Yes, that's exactly fine, in which case you can combine these two into this set, right? Does that answer your question? Yeah, that's a cleaner way of writing it. Any other questions? All right. Then let's see here. We've got 43 minutes left. Oh, okay. One more thing I wanted to go through was... Okay, this is literally the only thing I wrote down for this entire section, because there's a lot of stuff in 5.6 which I feel like is not really that relevant to you all, so I'm not going to make you learn it. I do want you to be exposed to this one, though, which is basically to say, look, I'm going to take a compressed version of the sine graph, okay? So here's like sine of x, okay? And then what does sine of 3x look like? It looks like it wiggles like much faster, okay? Something like this, right? I don't know if I did the requisite number of things. I think I did. Anyways, so it's going to wiggle a lot faster, basically. And so I want to find when is it going to be equal to 1/2. What I actually need to do here is to perform sort of like a change of variables. We already solved when is sine of... Okay, let me explain the following way. We already solved sine of t is equal to 1/2, right? That was given by the set t equals pi over 6 plus 2 pi. Okay, let me write it correctly. I shouldn't use shortcut notation if I'm going to ask you to use it correctly. Union t such that t is equal to 5 pi over 6 plus 2 pi n. N as in Z. Okay, so I'm just copying this straight down from here. We solved when is sine of x equal to 1/2. It gave us these two angles, which point at points whose height is 1/2. Those two angles are pi over 6 and 5 pi over 6. That is what we established in the previous example. Now we're supposed to find when is sine of 3x equals to 1/2. Okay? When is sine of 3x equal to 1/2? Well, what I really want is for 3x to be equal to t, which is either pi over 6 plus 2 pi n, in which case we can do, okay, or 3x is equal to t is equal to 5 pi over 6 plus 2 pi n. Okay, because then the input will be whatever values make this equation to be true. Okay, as long as 3 times my input is an input like this, then it will be the same as doing sine t. Okay, it will be the same as doing sine t. So this is called, this is kind of a change of variable type argument. Okay, so all I have to do to figure out what x should be is to take this equation and divide both sides by 3. Okay, so I take x then should be equal to t over 3, which would be pi over 18 plus 2 pi over 3 times n, or x is equal to t over 3 is equal to 5 pi over 18 plus 2 pi over 3 times n. N is in Z. I trust that you can formulate the correct set builder notation for that. Okay, you basically just do x such that, and then something like that. Okay. So this is just a cute kind of an example to find, well, look, you're trying to find when is the graph of sine going to intersect this height 1/2. Well, it's going to happen basically 3 times as many times for sine of 3x as it will for sine of x, okay? Because we have compressed it. It's wiggling much faster, so it's going to intersect this line many more times. Or more frequently, maybe, is the better way to say it. It's the same number of times for both of them, namely infinity. But yeah. All right, any questions on sine 3x equals 1/2? Okay, then if not, that's the last thing I wanted to teach you about trigonometric equations, and the last thing I wanted to teach you from Chapter 5. So let's recap what were the major themes of Chapter 5. So we started in 5.1 with trigonometric identities, right? So we learned a bunch of identities, and then what did we do? We moved on to proving and disproving identities. We saw the sum and difference formulas. We saw the half angle formulas. And then we had this trig equation stuff, which was how do we find the values which will cause a trig equation to be true if it's not an identity, i.e. it's not always true. So that is what we learned in Chapter 5. So a bit of a difference from Chapter 4, which was more about like computing the trigonometric equations for like a given angle input or something like that. Okay, so the last thing I'll teach you is something that you probably already know, which is called right triangle trigonometry. So if you took a geometry class in high school and you learned how to do trigonometry, this is probably what you learned, which is the same as what we have been doing. There's only just one small difference. So what does right triangle trigonometry say? Well, we have the famous saying, so katoa, Okay, if you haven't heard that one before, it's just a way of memorizing what is sine going to be. Sine, so SOH correlates with sine is going to be opposite over hypotenuse. Okay, so SOH means sine is opposite over hypotenuse. If you want the way to remember it, one of the ones that I heard was something like, some old hippie caught a high tripping on acid. I thought that was the most interesting one that I've heard, but there's a ton of different ways to remember SOHCAHTOA. This is the one I like because it really sticks in the brain. For me, anyways. So I don't know. Have any of you heard of a different way to remember it than that?
I think you just taught us a song.
Okay, there's the song, right? Anything else?
I did that one, but it said caught another hippie instead of caught a high.
Oh, okay. Caught another hippie. Interesting. Oh, so that's more of a judgment on the morality of of the process, right? Okay, that's funny. All right. Well, anyways, this is how you can remember it. So what does it say? It says if you have a right triangle, okay, if you have a right triangle, and you take one of the angles, which is not the right angle, okay, which is not the right angle, then sine of that angle will be the ratio of the opposite side to the hypotenuse. So what does that mean? By opposite, what I mean is if this is our angle theta, okay, then the opposite side is like across from that angle, okay? So you just go across from that angle. So the opposite side would be this side length here if this is our angle theta. Or if we chose theta to be in this corner, then the opposite side would be this side length, okay? So it kind of depends on which angle you choose to be theta. It could be this one or it could be this one, okay? But anyways, sine of that angle, okay, will be equal to the ratio of the opposite side length to the hypotenuse side length. So it makes perfect sense that this should be less than 1, right? This number is less than 1. Why should this number definitely be less than 1? Someone give me some reasoning for that. Why should this number definitely be less than 1?
Hypotenuse is the longest side.
Yeah, the hypotenuse is the longest side. That means that C is a bigger number than A. If you divide something by something which is larger than it, you get a number which is less than 1. Okay, so C is the longest side. Okay, same thing for cosine, except we use, instead of the opposite, okay, so this is the opposite. So we use the adjacent. So the word adjacent means next to. And by next to, there are two side lengths which are directly next to the angle theta. That would be namely C and B. But C we have already decided is the hypotenuse, okay? Okay, so the adjacent leg will be the leg which is not the opposite and not the hypotenuse, okay? That will be the adjacent leg. So this one is the adjacent. Okay, so we take that side length and we divide it by the length of the hypotenuse. We get cosine of theta, okay? And then for tan, we're going to take the opposite, which in this case would be A, and we're going to divide it by B, which is the adjacent. Okay, so you can use this to try to figure out like what are the side lengths of the triangle. If you know one of the side lengths, how do you figure out the others? Or you can figure out like what these angles are and stuff like this. And this process is called solving right triangles, okay? They give you like one of the angles and one of the side lengths, or one of the angles and two of the side lengths, I don't remember. But and then they ask you to find what is the other side length and also what is the other angle. Questions like this inside of triangles. which is exactly what we have been doing in the unit circle. The only difference has been we take our angle theta to be an angle inside of a triangle which happens to live inside of a unit circle. So what do we say? Well, we said that Jesus, I cannot speak. We said that this point has coordinates cosine of theta, comma sine of theta, right? For whatever that is. So, which is to say that, look, this length here is like B, and we can call this length here, or why don't I label it opposite? Okay, so this is opposite. This is adjacent. And what did we say that sine is? We said sine of theta is this opposite length over the hypotenuse. But what is the hypotenuse length? It's 1. So, sine of theta tells us exactly what is this length, because actually what it's technically telling us is what is the ratio of this length to the hypotenuse length. But since the hypotenuse length is 1, it's just going to give us what is this length in actuality. And that length is, of course, what we use to describe the y-coordinate of that point. Okay, so nothing new here. No, there's nothing new here. The only difference is we could make a triangle which would be bigger than this. Okay, you might have seen something like this on your homework if you clicked on the, like, help me with the homework problem or whatever. Well, the thing about this triangle is it's called similar. It's a similar triangle to this smaller one, meaning that they have the same interior angles. Similar triangles have same interior angles, and the ratio of the side lengths is preserved. Okay? So namely, if we call this side length A and this side length B, A divided by B will again be sine of theta. Okay, because we just take the opposite side length divided by the hypotenuse. And the ratio of A over B will be the same as whatever this opposite over 1 was, okay? The ratio will be the same. Okay, so this is the difference that we're going to have with right triangle trigonometry, is sometimes the hypotenuse won't be 1. Basically, that's the only difference for right triangle trigonometry. Any questions on this so far? Okay, well, it doesn't seem like there are, so let's do a quick example. Okay, so here is a problem that is using a right triangle that clearly the hypotenuse does not have length 1. So that's basically the only new thing here. So what am I supposed to do? I'm supposed to find sine of theta. Okay, well, that one's easy enough to do, right? Because sine of theta is just opposite over hypotenuse. And I know those two lengths. The opposite length is 2, and the hypotenuse length is 5. Great, I did a good job. Okay, so that's pretty simple. We just take the opposite length, which is 2, and we divide it by the hypotenuse length, which is 5. How about cosine theta? Well, for cosine theta, I know I'm supposed to take, I don't know, just write it here. Cosine theta is going to be adjacent length divided by hypotenuse length, which is going to be, I don't know what b is. Shoot. So I ended up with b over 5, but I'm supposed to find this explicitly, so that tells me that I need to figure out what b is, right? But I think you all know where this is going. How do I figure out what b is? Pythagorean theorem, right? Okay, so we do 2 squared plus b squared is equal to 5 squared, so that's 4 plus b squared is equal to 25, which means b squared is equal to 21. which means that b is equal to plus or minus the square root of 21. But of course, b is describing a length, so we're only going to take the positive square root. And 21, I think, is 7 and 3, right? So I don't think that can be simplified. Okay, now we're happy. Okay, so that's, I don't know, that's how you can solve a right triangle. You can figure out what the other angle is by doing something like sine inverse of square root 21 over 5. Okay, then you can, because square root 21 is this length here, which is the opposite. So if you invert the sine function, you can figure out what this angle alpha is. So alpha would be the inverse of the sine inverse of square root 21 over 5 would tell you what the angle alpha is. And then you'd know everything about this triangle. You'd know all the side lengths and you'd know all of the angles. And yeah, that's called solving a right triangle. Any questions on this example? Okay, then the last thing that we'll do for today will be this. So you saw the picture of the mountain. It's actually a moving image. I won't say whether it's a GIF or a GIF, but it's a moving image. Anyways, I thought we would enjoy it for a second before we just spoil it with mathematics. So people always ask me, like, when am I ever going to use this in my life or something like that? And I take issue with that for a number of reasons. The first of which is that I don't think that math is good for teaching you specific skills that you will use in your life in terms of like calculating the bill or something like that, or like doing your taxes. What math does for you is it teaches you something of like how to think and how to like reason, right? So, you could say the same thing of like a, Olympic sprinter, right, who wants to like run really fast. And you could say, look, why on earth do you go to the gym and squat 500 pounds on your back? When are you ever going to do that in a race, right? When are you ever going to do that in a race? You're not going to do it in a race, but what is it? It's some kind of training, right? It's in order to strengthen your muscles so that when you go out and then actually use them, they're stronger, right? Same thing with math, but for your brain, okay? But anyways, I always like to put in something when I can to show you that this stuff can be used for an actual reason. So let's say that you know how tall some ledge is, like up here, and you're wondering, well, I've been up to that ledge, and I've always wondered how tall is the mountain itself, right? How tall is the mountain itself? Okay, and let's say that you have some kind of, I don't know, like laser measuring device, so you can point a laser from here to here and measure that this distance here is 5 miles from this ledge to that ledge. And you know that the elevation of that ledge you were standing on was 8,720 feet. And you want to know how tall is the mountain itself. Okay, well, we can use right triangle trigonometry to solve a problem like this. Okay, so basically the way we're going to do it is we're going to say, ooh, that's not a good color to use here, is it? How about purple? Okay, we're going to check what is this length, which let's call it x, and we're going to add that to, we're going to take x plus 8,720 feet. That will be this whole length here, right? So we just need to figure out what is this length right here, right? Well, we can solve for x in a fairly straightforward manner by doing the following. We take sine of 23.75, which we can do on our calculator, is equal to x divided by 5. So x is equal to 5 times sine of 23.75. So let's bust out the calculator. I know this is wild because I've never asked you to use a calculator to do a trig function.
Oh, we're supposed to use calculators in this class.
We're not, but this is just to show you. Okay, when I do this, on my calculator, I get 2.013. Okay, so, and some other stuff. Let's just call it about 2. Okay? Close to 2. So then, do we agree that the height of this mountain should be 8,722 feet?
No.
Approximately? Someone says no vehemently. Why not?
Because the 2 is in miles, not feet.
Exactly. The length I used here, okay, was 5 miles. If I wanted to solve for x in terms of feet, I needed to take 2 multiply by, what is it, like 5,280? Is that right? Okay, so let's see. That would be 10,560, right? Okay, so the height of the mountain is actually 8,720 plus 10,560, which is like 1,900. No, sorry, 19,000. And then what do we do here? That should be 280. Jesus, this is hard. Okay. You see why I don't like to do problems like this. It just comes down to arithmetic. But anyways, there you go. So this is a very practical thing that you could actually do. You can use a device that's, I think it's called a sextant or something like that, to measure an angle of like from, you just point something parallel and then you measure the angle, you just point it up until it's pointing at this thing. You can measure the angle of where you are to where something else is. So you can figure out what is the height of a flagpole or a mountain or a tree or whatever from far away without actually having to like go to the top. Okay, so let's say you had like a tree over here and you want to know how tall it is. Well, you can just measure this angle here, which is easy to measure using a sextant, and you can measure how far it takes you to walk from here to here. Okay, and then what could you do? You could say, look, if this is x, I want to know what x is, I know what y is. You could say, oops, I should not call him that. I should say, I want to know what y is, and you know what x is, and you know what this angle theta is. You can relate these things by saying, look, not sine, but tangent theta would be equal to y over x, right? And you know what x is, and you know what theta is. You can do tangent now using a calculator if you want. To figure out y, you just take tangent times x, right? Tangent theta times x. So you can use that to measure something without having to actually climb it, or like take your measuring tape from top to bottom on this thing, which is sort of intractable for a lot of tall things, right? Okay, any questions on this one? All right, then that's it. That's all I wanted to teach you. So we can end it early for today. But before we pack up really quickly, I just want to remind you all, I'm going to have office hours today from 2:30 to 4 in LeConte 109. Thursday, same time. Tomorrow in class, Thursday in class, we'll spend reviewing. Okay, so we'll do a very comprehensive review. Please come with questions.